Okay, so today is we're in our third week now, and it's Monday, and we are going to continue talking a little bit more about confidence intervals, and we'll also introduce hypothesis testing, which is in chapter 7. So let's take a look. Okay, so one thing we can talk about is, sometimes when you do a study and you want to make a confidence interval, in order for your confidence interval to be kind of useful, maybe the margin of error has to be within a certain size. Okay, so if you don't want your margin of error to be super wide, because again, confidence intervals that are very wide or have a very large margin of error aren't going to be that useful, right? So for example, if there is, if an election's coming up and you want to know, okay, who's gonna win, right? So, for example, there's like a recall election coming up in California and things like that. And I don't know what the polling data is, but if a poll is published and it says, oh, percentage supporting this is, 45% with a margin of error of 15%, that's not a very useful interval, right? Because 45% with a margin of error of 15% means the true number could be anywhere from 30 to 60%, which is a huge swing, right? It's a huge difference between 30% support and 60% support. And so having a very large margin of error is not going to be useful. So we need something with a little bit of a smaller margin of error. 45% with a 2% margin of error, that says something, right? That goes anywhere from 43 to 47%, and that's less than a majority or something. And so whatever it is, whatever topic or issue or candidate you're talking about, generally smaller margin of error is more useful, right? So let's say we wanted to make a confidence interval for mu, the population mean. We often have to decide how many data points, how large our sample should be, right? And so the resulting standard error for the mean is going to be S divided by the square root of n, okay? And so the width of the interval, which is going to be plus or minus, your critical value t multiplied by the standard error, the width of the interval and that margin of error is going to depend on basically the standard deviation of your observations and the sample size. Now, we don't have very much control over the standard deviation of our observations. That's just going to be a property of the data. So, whatever population we're looking at, the property of the data, you might have a big S, you might have a little s. We don't have much control over that, but we do have control over how much data we are going to collect. We have control over our sample size n. Now, there are practical considerations that we might have to consider. For example, if you're running some kind of experiment, each data point you collect costs you money, right? It requires time to collect that data point. You've got to hire somebody who's qualified to gather that data, and so every observation, costs, requires additional money and resources and time to collect. So there might be a practical limit on exactly how much data you can collect. But let's say you have a certain margin of error that you want, right? Your desired margin of error, and you have a certain confidence level that you need, right? So from there, you can kind of solve backwards for how large your sample size is going to be, right? But that's going to require that you need to guess how large your the standard error or the standard deviation is going to be. This should actually say SD, standard deviation. Okay, so this requires you to guess how large your standard deviation, which is, that could be based on either a preliminary study or a preliminary sample, maybe some previous experience, or you could try to look up some existing literature on the subject, right? There's, several moving parts here, and, changing your sample size, increasing n does affect what your t-star is going to be, right? With a smaller sample size, you have, you're generally going to have a larger t-star, and with a larger sample size, t-star is also going to get smaller. In any ideal scenario, we try to gather as much data as we can. But again, you don't want to be wasteful with your resources. You don't want to do overkill in how much data you're going to gather. But but doing a preliminary check could also show you that you don't have enough funding to even do the study that you want, right? So for example, you might say, maybe you're trying to write a grant proposal and you're saying, we need money to do this kind of study, and for it to be worth our time, we're going to need to collect at least this many data points, say 2,000 data points or something. And to collect 2,000 data points, we need, this many thousands of dollars. And they might come back and say, well, no, that's too much. But a smaller scale study just might not be useful, because it could just end up with a margin of error that's too big. Okay. It is important to remember that whatever we're doing, when we do confidence intervals, and then later on today, we're also going to look at the hypothesis test. Excuse me. These ideas revolve around the central limit theorem, and we talked about the central limit theorem earlier. And that's the idea that no matter what your population looks like, if you take a sample that's large enough, that resulting the sampling distribution looks like the normal distribution, right? And if the sampling distribution follows the normal distribution, then we can do our inference where we can say, we expect the sample mean to be close to the population mean. And we can flip that around and we say, if we observe the sample mean located here, we can be confident that the population mean is nearby, right? If we see the sample mean is located at the 30, just like if we see the dog located at the 30, we can be confident that the invisible owner is nearby. We can be confident that the population mean is nearby, okay? But in order to apply the central limit theorem, there are a couple kind of key criteria that need to be met, right? Number one, it has to be reasonable to think of the data as a random sample drawn from a large population. If you're looking at this design of your study, and it is unreasonable to regard it as a random sample, then we're going to run into problems, right? To be honest, you will very rarely come across a study where the design is truly random. Okay, so that might not be possible, but they could say, we looked at these patients from this area and also from this other area, and therefore we got kind of a wide, a diverse group in our in our sample, and therefore we can kind of generalize to a larger population, right? So the reality is a true random sample is very hard to come by, but it has to at least be reasonable to think of our sample as either a random sample or a representative sample, right? If the study only looks at one small segment of the population, it would be quite dangerous to then generalize to the general population, right? So if you're only looking at people over age 60, you don't want to take those conclusions and generalize to the entire population of all ages, right? Maybe you can generalize to all other people over age 60, but anything larger than that sounds not like a good idea, okay? And then the other part is the sample has to be large enough, right? So again, we always want to be working with large samples or samples that are big enough. But if, and the rule of thumb is that if the population is not normal, then n must be large, where n being greater than 25 is good enough for most cases. But if you do have a normal population, you can get away with a smaller sample. So you could have, sample size of 10 or 15 or something like that, if it's reasonable to think of your reasonable to assume that the population is normally distributed. Okay. All right. So I hope that's okay. That's just kind of some conceptual ideas regarding kind of the validity of using confidence intervals. And what we're going to do now is we're going to talk about confidence intervals, but use them to compare the means of two populations. Okay, so when we first introduced a confidence interval, it was, you taking one sample, and based on this one sample, what can we say about the mean of its respective population? And now we want to take a look at two samples and make conclusions about two populations. Okay. Before I get into that, let me go ahead and give you your first view quiz answer for today. Today's view quiz answer is the letter D. D as in dog. D as in dog is your first view quiz answer for today. All right, so the idea here is we are looking at two samples of data. And what we want to ask is, based on these two samples, do the respective populations have different means, right? So you have sample one, it's got some mean. You've got another sample taken from like another group, and it has a different mean. And the question is, okay, if my two samples have different means, does that mean their respective populations have different means? Or, is it possible that the respective populations have the same mean? Okay. Now, so illustratively, this is kind of the idea that we have. You've got population one. Again, the populations are big entities that we are unable to observe directly, right? So, for example, population one could be everyone from California, and population two could be everyone from Texas or something like that, right? And so you have the entire population, and it's too big to observe the entire population of California, and population two being Texas, also too big to observe the entire population of Texas. But what we're going to do is we're going to take a random sample from population one and a random sample from population two, sample one and sample two. Sample one has certain summary statistics. You observe, however, the two samples don't have to be the same sizes. So sample one has a size of n1, and it has a mean x bar 1 and standard deviation s1. Sample two has its own summary statistics. It might have a different size, n2, and it's got its own mean x bar 2 and standard deviation s2, right? And we are able to observe the values in those samples. We're able to observe the sample statistics, but we don't know what the respective populations are. And what we want to ask is, could the mean of population one, we're going to call that mu1, and the mean of population two, call that mu2, could those two values be the same, or do we have evidence that the mean of population one is different from the mean of population two? Okay, because we know that our samples are subject to random forces, right? So, it's possible that population one and population two have the same mean. You draw a sample from population one, and that sample, for whatever reason, has a mean that's too low. And you draw a sample from population two, and for whatever reason, again, just because of random chance, its mean is too high. And so when you compare the x bar 1 and x bar 2, there's a difference, but in reality, the two populations actually have the same mean. So that's a possibility, okay? On the other hand, it could be that population 1 and population 2 have different means, okay? And so we want to create a confidence interval for that difference, for the difference between mu1 and mu2. Okay. Question. The first view quiz answer was the letter D. D as in dog. D as in dog was the first view quiz answer. Okay. So this is our question here is based on our samples. What can we say about the quantity mu1 minus mu2? So So that quantity, mu1 minus mu2, represents the difference between the population means, right? So population 1 has mean mu1, population 2 has mean mu2. Mu1 minus mu2 is the difference between the means of the two populations. And so effectively, we want to ask, could the difference between mu1 and mu2, could that difference equal 0? Okay. And if the answer is if the difference could be 0, right? Basically, if the difference is 0, that means there's no difference, right? Then that means if that difference could be 0, it's possible, or it could be that the populations have the same mean. That's what it comes down to. Okay. On the other hand, if we come back and we say, yeah, no, we have evidence that the difference is not 0, right? So we have evidence that the difference between mu1 and mu2 is not going to be 0, then we would say we have evidence that the two populations have different means. Okay. So I kind of want to make sure that makes sense, because this is going to be central for us going forward. Okay. So could that difference be 0, or do we have evidence that it's not 0? Okay. And again, and it's a little bit strange to think about, but the difference itself, and we could call it D, but mu1 minus mu2 is the difference, and that's the parameter that we want to estimate. Okay. We're not going to be able to get an exact value for this quantity. Okay. Again, because we don't have access to the population, just like we're not able to locate the exact location of the invisible owner. Okay. But what we're going to do is we're going to create a confidence interval for that parameter, the unknown parameter, and that's going to kind of represent the range or the interval of plausible values for that difference. Okay. We got a question in the chat. The question says, if it is 0, if the difference is 0, we have evidence that the means are the same, or it could be the same. Okay. Yeah. So the question is, if the result of your interval, all right, the result of your study says that mu1 and mu2 could equal 0, that's all it says. We're just saying that it could equal 0. We're not saying it's definitely equal to 0. We're just saying it could equal 0. And if it could equal 0, then that means there could be no difference. Okay. If the difference could be 0, all we're saying is that it's plausible. It's plausible. It's not. It would not be a shock to us that if it were 0. Okay. All right. So just a simple example here. Let's say we take 2 independent samples. Okay. We get some adult men and adult women, and we measure their heights, right? We have a sample of adult men, self-identified men and women, and we just say, all right, thanks for volunteering. Let's just measure how tall you are, right? And so if we were to make a 95% confidence interval for the difference between mean heights, okay, that confidence interval, I'm just making up numbers, but it could be something like 4 to 8 inches, okay? Our 95% confidence interval could be, for the difference, could be 4 to 8 inches, okay? And what that means is we're going to say something like this. The interpretation of that confidence interval would be, I'm 95% confident that the average height of adult men, okay, the average height of adult men in the population is somewhere between 4 to 8 inches taller than the average height of adult women, okay? We're not saying anything about individual men or individual women. We're not saying anything about the sample of men or the sample of women, or even the mean height of men or the mean height of women. We're only saying something about the difference between mean heights. So we're saying, if it's a little bit of a ridiculous idea, but if you could think of like, what is the quote unquote average man, okay? Being, this would be a man who is of average height and of average weight and of average whatever. And we think of what is the quote unquote average woman, again, a person who is of average height and average, whatever else. What would the difference between what is their height difference? The average man versus the average woman, what's their height difference? And what we're saying is we're 95% confident that their height difference is going to be somewhere between 4 and 8 inches, okay? That the quote unquote average man, if such a thing existed, would be somewhere between 4 inches taller and 8 inches taller than the average woman. Again, if such a thing existed, okay? So this confidence interval, again, doesn't say anything about the average height of men alone, which is probably something around, 70 inches, 5'10", and doesn't say anything about the average height of women alone, which is something around 64 inches, 5'4", something around there. It's a statement about the difference between the averages, okay? And the key here is that our confidence interval is entirely positive. We're saying it goes from 4 to 8, right? And so 0 is not between the ends of the interval, right? The interval does not contain 0. And what that means is we have evidence that the difference between the population means is not 0. Or in other words, we would say we have evidence that the height of the average man is not going to be the same as the height of the average woman, okay? And again, we're not saying anything about individuals, because you could definitely, if we're talking about individuals, you could find a man and a woman who are the same height, okay? And you'll even find many women who are taller than many men, and that's not an unusual thing if we're talking about individuals, okay? But what we're just saying is if we were to take the average height of all men and the average height of all women, what we're saying is we have evidence that those two numbers, the average height of men and the average height of women, are not going to be the same number, okay? And based on our interval, we're saying, we're confident that the average height of men is higher than the average height of women. Okay? And so we would conclude that we have evidence that there is a difference between population means. Okay? Is that okay? Does that kind of make sense, what we're stating there? And so this is kind of the idea that we're going to implement. And we're just making confidence interval for the difference, not individuals or anything like that, okay? The formula is this, all right? And I'll give you the formula. And again, I think the formula is probably the easiest part of anything, is you just kind of take your summary values and you just plug them in, and it's a matter of just being able to type this into your calculator to get the issue, or the values, right? This part inside the square root is the standard error. That's our estimated standard error. It's S1 squared divided by N1 plus S2 squared. So standard deviation of sample 2 squared divided by N2, the size of sample 2. Okay, you add those things together and you take the square root. And then when you multiply the standard error by your critical value T star, that becomes your margin of error. This entire part that goes plus or minus is going to be the margin of error. Okay, whereas the difference between your two sample means, y bar 1 minus y bar 2, that's going to form the center of your interval. All right. When we look up the critical value T star, we need to know the degrees of freedom, right? We need to know what confidence level we want to choose, probably 95%, but sometimes 90%, sometimes 99%, sometimes something else. Okay, so you pick your confidence level, but you also need to know your degrees of freedom. The truth is that the formula for the actual degrees of freedom, when you have two independent samples, it's rather complicated. Okay, so we're not going to bother, as far as doing things by hand, we're not going to bother with figuring out the actual degrees of freedom. If you want to use your computer, the computer can figure out the degrees of freedom it should use, no problem. But if you're, for quizzes and things where we do things by hand, it's kind of too much work to do it by hand. So we're going to just use an approximation. Okay, we're just going to take N1 plus N2 and subtract 2. So it'd be like degrees of freedom for sample 1 is N1 minus 1. Degrees of freedom for sample 2 is N2 minus 1. And then we're just going to add them together. Okay, and so we're going to get N1 plus N2 minus 2. Right? This it's an okay approximation, but it's always generous. Okay, the actual degree of freedom is always going to be smaller than N1 plus N2 minus 2. Okay, less than or equal to, I should say. All right, so N1 plus N2 minus 2 is always going to kind of be an upper bound for the degrees of freedom And in reality, the actual degrees of freedom is almost always going to be a little bit less than n1 plus n2 minus 2. Okay, so what we're going to do is, sometimes you might end up with something like, let's say you have a sample of size 20 and another sample of size 20. You've got two samples of size 20. So if you follow the formula for the degrees of freedom, you're going to get 20 plus 20 minus 2, you'll get 38 degrees of freedom. Okay. Now, when we use our reference tables, pull up my reference tables here. Okay, so if we go to the T table, and so let's say we had two samples of size 20, 20 plus 20 minus 2 is 38 degrees of freedom. You don't find 38 degrees of freedom in the degrees of freedom column, okay? You find 30 and you find 40, okay? And so again, because 38 degrees of freedom is a generous number here, what we're gonna do is we're always gonna round down, okay? So even though 38 is closer to 40, we would round down and just use the row for 30 degrees of freedom, okay? Because this approximation n1 plus n2 is always a little bit generous. So if the actual degrees of freedom is not found, always round down, okay? Other books might recommend a more cautious approach. And they would say, don't use n1 plus n2 minus 2, just use n minus 1. And because you have two values for n, just use the smaller of n1 and n2. And that will always be kind of your, that'll be like the stingy version of the degrees of freedom. That's always going to have fewer degrees of freedom than what it actually is. And the true answer is somewhere between the stingy answer and the generous answer. And we'll just go with the generous one and round down. That'll be kind of our thing. Okay. All right, so let's look at a couple examples, or let's just look at this example, and we'll revisit this example later today when we introduce hypothesis tests. Okay, and so I completely made up this example. I don't even know if this is if this would be legal for a company to do, but maybe it's fine. Maybe the test is fine, but then to like study based on ages, maybe that's not so good. Okay. But basically, there's some test for dexterity. I don't know. Have you guys ever played the, it's like a kid's game called Perfection. And there's like a little blue tray that you push down and you fit the shapes in, and there's a timer clicking. And if you don't get it in, it explodes. No? Okay. Well, anyway, I'm just imagining some test, some company giving its applicants a test for doing something like this. And I don't know if such a thing would even happen, but they're going to say there's a whole bunch of different funny shaped blocks. The applicants have to kind of rotate them in order to get them to fit into a hole. They get 1 minute to do this thing. And there's a whole bunch of of these blocks. Okay. And so they get, we're going to have 20 young adults. I guess that will be young adults. I don't know, maybe adults in their 20s. And then 15 seniors. So we'll say seniors, people over age 65. Okay. We're going to assume normality as far as their abilities go. Okay. And so we're going to say, when we look at the data among the 20 young adults, the average number of blocks that they were able to complete in that 1 minute period was 28.2 blocks with a standard deviation of 4.3. Oh, okay. One person put in, my childhood anxiety when the shapes pop out. Yeah. I don't know. I love playing that game. So anyway, and then the average number of blocks the seniors were able to complete was 24.3. You know what? I'm going to side note. We're going to go on Amazon, and I got to show you what this thing looks like. All right. So Amazon. Let's go. Okay, it's kind of like this. Where is the thing? This is like not an exciting version. Where is the real thing? Is this it? Yeah, it's okay. Here it is. And so you put the pieces in, you get 60 seconds. This one has 25. You got 25 shapes to fit in, and you got 60 seconds to do it. And you think, oh, that's kids play, but maybe you can do it, maybe you can't. Okay, well, anyway, so So I'm just making up stuff here. Can I look up the alligator teeth game too? All right, were we just browsing Amazon today? Okay, so so here's perfection, the alligator teeth game. Oh yes, it's yeah, you try to it randomly triggers the thing to snap down and bite your hand. This is not the real Aishan. That's not Hasbro Crocodile Dentist. Okay, so this is the original. 21 bucks. That's more than I remember. Look at all these ratings here. Okay, well, they're having fun. All right. Anyway, okay. And then we're going to say the seniors were able to complete an average of 24.3 with a standard deviation of 5.7. Okay, so young adults on average were able to complete 28.2. Seniors were able to complete an average of 24.3. All right, so this was based on a sample of 20 young adults and a sample of 15 seniors. Okay, and so these are, we'll say these were randomly selected young adults, randomly selected seniors. Now, the question is, okay, our sample has 28.2 versus 24.3. So that's a difference of a little under 4, right? It's a little difference of a little under 4, maybe 3.9. And the question is, does that mean if we looked at the general population of young adults versus the general population of seniors, is there going to be a difference between the average number of blocks that they can complete? What do you guys think? Okay, so because it's also possible, someone could argue that, oh, you know, just by random chance, you got some high performing young adults, and that's why they were able to complete 28.2. And you got some low performing seniors, and that's why they were only able to complete 24.3. It's a valid argument, maybe. Okay, so, or is this difference between 24.3 and 28.2 can't be explained by just kind of this random sampling, but just like, no, and really the young adults can do more than the seniors as far as blocks go. Okay. Just kind of want to get a pulse for what you guys think based on these numbers. Give me, we'll say what are our possible reactions? Okay, give me a green check if you think there is a difference in the population, and will give me a red X if you don't think there's a difference in the population. I'm just curious what you guys think based on these numbers that I've completely made up. Okay, so some people are giving me green. We got about 9 to 10 to 5, 11 to 5, around a 2-to-1 ratio, 12 to 6, 13 to 7, 14 to 7. Okay, so it seems about 2/3 of you think 28.2 versus 24.3 is indication of an actual difference. And then maybe a third of you, maybe a little bit less, think that that difference isn't big enough for us to make that conclusion. Okay, so well, we'll take a look. Okay, these are the respective standard deviations, and so so what we're going to do is we're going to make a 95% confidence interval. Okay, so I guess, you know, before I just go cut straight to the answer, I guess we'll plug in our numbers. Oops, that's the other class. And all right, so let's go ahead and okay, so we have sample 1 will be the young adults. Okay, and so we have 20 people. We have the average is 28.2. The standard deviation 4.3. Okay, as far as the other side, we have seniors. We have 15 of them. N2 is 15. Our Y bar for the seniors on average was 24.3. And the standard deviation 5.7. Okay, and I'll just flip back a few slides. The formula for the confidence interval is Y bar 1 minus Y bar 2 plus or minus T star square root of S1 squared over N1, S2 squared over N2. Okay, and okay, so our degrees of freedom, N1 plus N2 minus 2. I've got 20 plus 15 minus 2. I have 33 degrees of freedom. We'll go to our T table. So we don't find 33 degrees of freedom, but we'll round down and use 30 degrees of freedom. 95% confidence, 30 degrees of freedom. My eyes are playing tricks on me. 2.042. 2.042. That's going to be the T star we're going to use. 2.042. So from the table. Okay, and so now it's a matter of just plugging in the numbers we have. So y bar on 28.2 minus 24.3 plus or minus 2.042 multiplied by the square root of S1 4.3 squared over N1 20 plus S2 squared 5.7 squared over N2 15. So the question is, do you always round down degrees of freedom? Yes, always round down, just because this approximation, N1 plus N2 minus 2 is always a generous approximation. It's going to always overestimate the degrees of freedom. So to kind of compensate for that, we're just going to round down. Okay. There is a formula that's more accurate, but it's a pain in the butt. Yeah. So even if it was 39 degrees of freedom, yeah, just use 30 degrees of freedom. Okay. At least if you're using this approximation. Okay. So we have 3.9 plus or minus 2.042. And then let's figure out what our standard error is. Standard error is 4.3 squared over 20 plus 5.7 squared over 15. Okay, and that's 1.75798. So 1.758. 3.9 plus or minus. All right, so let's do 2.042 times 1.758. 3.589. 3.5. I'm just going to do 59. Okay, 3.9 plus or minus 3.59. Okay, so on the lower bound will be 3.9. 3.9 minus 3.59. I get 0.31. And then on the upper side, 3.9 plus 3.59, and that gives me 7.49. All right, is that okay? Plugging everything in. So that's what we get, 0.31 to 7.49. Plugging in our values here. Okay, and then so our conclusion is we're going to say we are 95% confident that on average young adults can complete between 0.31 and 7.49 more blocks than seniors on average, right? So the average young adult can complete somewhere between 0.31 and 7.49 more blocks than the average senior. Okay. And so because our entire interval is positive, 0 is not within the bounds of the interval, we're going to say we do have evidence that there is a difference between the average number of blocks completed by the two groups. Okay, so that this difference of 3.9 is big enough for us to say that, yeah, there is a difference between the average number of blocks completed by young adults and the average number of blocks completed by seniors. Okay, even though we only looked at a small sample of 20 young adults versus 15 seniors. All right. Do we feel okay about this? So we're saying 0 is not in the interval. 0 is not between the lower and upper bounds. Okay. The question is, what if we swapped group labels, right? So when we did this, I called young adults group 1 and seniors group 2. Okay. What if we had swapped it around and we had seniors be group 1 and young adults be group 2. So what would happen is, okay, so we're going to call this N2, Y bar 2, S2, and this would be N1, Y bar 1, and S1, okay? And then so the answers would be the same, right? We're just going to do 24.3 minus 28.2, okay? Plus or minus, T star is going to still remain 2.042. And when you take the square root, you know, we'll swap positions, 5.7 squared over 15 plus 4.3 squared over 20. But that, you know, this ends up being exactly the same, right? This is still going to end up being 1.758. This is 2.042. And so we're just going to get negative 3.9 plus or minus this. And the interval is going to go from negative 7.49 to negative 0.31. It's just going to become kind of the negative. Did I have to put on average twice here? Let me see. Confident that on average, seniors on average. I mean, I guess it's a little bit redundant. It's a little bit redundant to put on average in there twice, but I guess I wanted to really emphasize that we're just talking about the average. We're not talking about an individual young adult and an individual senior, because you might find, you know, one individual young adult who completed only like a few and one of the seniors who completed a lot. We're not saying about anything about individuals. We're just talking about on average about the entire groups, okay? But yeah, it is a bit redundant to write on average twice in there, but that's what we have. So if we swap the group labels, everything else is going to remain the same. It's just this part's going to become negative 3.9. And so the resulting interval will become negative 7.49 to negative 0.31. That's going to be the resulting interval, right? And so here, if we were to make the interpretation, we would say something like, or 95% confident that on average seniors can complete between 0.31 and 7.49 fewer blocks than young adults on average, right? The average young adult versus the average senior. So over here we said young adults can complete between this and this more than seniors. And over here we're saying seniors can complete between this and this fewer than the young adults. And so it's the same thing, right? One, we're saying, basically we're saying group 1 is bigger than group 2, or we're saying group 2 is smaller than group 1. So same answer, maybe the point of reference has changed. And again, the idea here is because 0 is not within the bounds of the interval, we're going to say we do have evidence that there is a difference between the average number of blocks completed by the two groups. Okay. So there is a difference, or we do have evidence of a difference. Okay, does that feel okay? All right, what happens if we make a 99% confidence interval? All right, so here, you know, here's our 95% confidence interval. If we expand and we make a 99% confidence interval instead of a 95% confidence interval, then the only thing that's going to change really is going to be the critical value T star. So if we go to our T table, we're at 30 degrees of freedom. We go to the column for 99% confidence. So rather than 95% confidence, we go to 99% confidence, and we use the critical value 2.750. Okay, 2.750 is the number we use for 99% confidence. Okay, so it would be 3.9 plus or minus 2.750 times our standard error. Our standard error uses the same numbers, S1 squared over N1, S2 squared over N2. 1.758, okay, and so if we work that out, we're going to get 3.9 plus or minus 4.83. All right, and so if we take the lower bound, 3.9 minus 4.83 gives me negative 0.93. 3.9 plus 4.83 gives me positive 8.73, okay? And so if we want to be 99% confident, okay, our interpretation becomes a little bit kind of wonky. It says we are 99% confident that in the population, the mean number of blocks completed by young adults is between 0.83 blocks fewer and 8.73 blocks more than the mean number of blocks completed by seniors. Okay, so we're saying I'm 95% confident that the young adults can complete something that's between, less than or more than the seniors, okay? And so if we want to be 99% confident, okay, well, we're not able to say that there's a difference between the population means. Okay, 0 is within the bounds of the interval, right? The interval goes from -0.9 to positive 8.7, okay? 0 is inside the bounds of the interval. Which means 0 is a plausible value for the difference between mu1 and mu2, okay? The difference between mu1 and mu2 could be 0, meaning that it's plausible to say that there's no difference between the means of the two groups. Again, this is if we want to be 99% confident, right? Because when you want to be more confident about the answer and the conclusions you're giving, you got to be a little bit more cautious about making any kind of claims, right? So if we're going to be 99% confident, then we have to say we don't have evidence or enough evidence to conclude that there is a difference between the population means. So again, same data, different conclusions, because we have different levels of confidence, right? If we're only going to be 95% confident, okay, we can say, oh, you know what? Here's my interval. 0 is not within the bounds of the interval. I can conclude that there is a difference between the average number of blocks between young adults and the average number of blocks completed by seniors. If you want me to be 99% confident about my conclusions, right, I got to be more cautious. And I got to say, well, you know what? Based on the interval I have, I could believe, right? It's plausible that the average number of blocks completed by young adults is the same as the average number of blocks completed by seniors. So if you want me to be 99% confident, I'm not ready to say, that we have evidence that there is a difference between the population means. I got to say that, I don't have enough evidence right now, right? My sample of 20 and sample of 15, that's not enough evidence to conclude that there is a difference between the two groups. Right? Is that okay? So over here, we do have 0 in the interval. So we have to say we don't have evidence between the groups, right? Question, do we need to add on average in the interpretation? Well, here, because I'm using the word the mean number of blocks, okay? Because so I'm using the mean number of blocks. And so, so that kind of substitutes the question for on average, okay? Here, question, can we say that we know the means are the same based on our evidence? So the question is, can we say that because 0 is within the bounds of the interval, that means that the means are the same? And the answer to that is no, okay? We're never allowed to say that the means have this value or the difference between the means is this value. We're not allowed to say that the difference between means is exactly equal to 0 or something like that. All we can say is that we don't have evidence of a difference, or we do have evidence of a difference. We're not allowed to say this is the number, okay? That's how confidence intervals work, okay? We're not allowed to say that the difference is this, right? Okay, so I think I've already talked about this, right? Despite the 99% confidence interval coming to a different conclusion from the 95% confidence interval, the results are not in conflict. If we want to be 99% confident in our statement, we're more cautious about making any kind of conclusion that says that the two groups are going to be different, right? At 95% confidence, we can be a little bit less cautious, and we're ready to make a conclusion to say that the two groups are different. Okay. I put this and I said your turn, but I'm going to just go ahead and skip over this, and you can do this in your homework and on your own time. Okay. I want to talk about statistically significant versus actually important. But before I do that, let me give you your second view quiz answer. The second view quiz answer is the letter A as in apple. A as an apple is the second view quiz answer for today. Second view quiz answer is A as an apple. All right, so we are going to say if, so back when we made conclusions, we said if the confidence interval doesn't contain 0, right? If it's like it goes from 0.39 to 7.53 or whatever it is, we say we have evidence that mu1 is different from mu2. We have evidence that there's a difference between the mean number of blocks that the young adults and the mean number of blocks that the seniors are able to complete, okay? Other things that we can say is we can say that the difference between our samples, y bar 1 and y bar 2, is statistically significant. So when we looked at our data, you know, the young adults completed 28.2, the seniors completed 24.3. That's a difference of 3.9. And we can say the difference of 3.9 is statistically significant, okay? Or we can say that y bar 1, 28.2, is statistically different from y bar 2, is 24.3, okay? We can say that those two numbers are statistically different, okay? But here's the thing, statistically significant does not mean that it's actually important, right? Just because things are different doesn't mean that the difference actually is important, okay? If a difference is significant or statistically significant means that the difference is unlikely to be a result of random chance alone, okay? It's unlikely to be a result of random chance alone. And whether or not a difference is actually important actually depends on the situation, requires someone who's knowledgeable of the subject. Okay, all right, someone said their Wi-Fi cut out. So the second view quiz answer is the letter A. A as an apple is your second view quiz answer, all right? A as an apple. Okay, so I just want to kind of give you an example of this, right? The difference between statistically significant and whether it's actually important, okay? So this is an example from crop yield, and group 1 is yield with fertilizer, and group 2 is going to be yield without fertilizer, right? So let's say you're a farmer. I don't know anything about farming, okay? My entire knowledge of farming comes from like Stardew Valley. So I don't know anything about farming. It's just, but we're going to say, you know, you can apply fertilizer and maybe that's going to make your crops to grow bigger, okay? Or better, who knows, okay? And maybe a company says, hey, you know, you should use our fertilizers because that's going to improve your crop yield, right? And maybe you say, oh yeah, that would be great. But how much is it going to cost? And they say, well, in order to build the systems that are going to distribute the fertilizer and all of this, it's going to cost you, you know, X thousands and thousands of dollars, right? And you say, oh, that's a lot of money. In order for that investment to be worth it, okay, I need to see a gain of at least, I don't know how you measure crops, but we're going to just say like 1.0, whatever per whatever, okay? So we're, you know, they measure their crops in something, right? Bushels of something per acre, okay? And we're going to say, you know, we need to see an improvement of at least 1.0 in order for it to be worth it, right? Otherwise, you know, it's nice that I'm spending all of this money, but if I'm getting something like only 0.7, even if it's an improvement, it's not going to help me break even, right? As far as the cost, right? And so so that requires, right, this number, figuring out that we need to have a number of 1.0 whatever bushels per whatever acre per day or whatever, that number, to use this value 1.0 to separate what is worth it versus not worth it, that requires an expert, right? That requires somebody knowledgeable on things like finance and return of investment. That's going to require somebody knowledgeable at least on like farming systems and things like that. So somebody with an expert opinion needs to come up with this number 1.0, okay? As far as us doing statisticians, you know, all we can say is just like, oh yeah, you know, this is a difference, okay? This is a difference and not, it's not due to random chance, but we can't say if it's actually important or not. Okay, so I've got a few kind of results here, and perhaps it'll help if I draw a number line. Okay, so all right, so here we're going to put say 0. This is 0, and this is going to be 1.0. Maybe that's too far over. Okay. 1.0, 2.0, 3.0. Okay. All right, so our first confidence interval goes from 0.2 to 0.3. Okay, our first confidence interval will go from 0.2 to 0.3, which goes somewhere from here to here. Okay, 0.2 to 0.3, right? And so 0.2 to 0.3, we're going to say, is that statistically significant? And the answer is yes. 0 is not inside the bounds of the interval, right? So here we have a difference that is statistically significant. We say, oh, when I implemented the usage of the fertilizer, yeah, my crops got bigger, and I observed a gain of 0.2 to 0.3 in the crop yield. Okay, so that is statistically significant. But is it important? And the answer is no, it's not going to be important. It's not worth it, right? In order for it to be worth it, it's got to pass 1.0. It's got to be above 1.0. And this is kind of the worth it threshold in order for it to be worth it. And even in the best case scenario of like getting 0.3, it's less than 1.0, right? So even in the best case, it's not over 1.0. So it's not going to be worth it. Okay, let's take a look at another interval, right? So another interval goes from 1.2 to 1.3, 1.2 to 1.3, okay? 1.2 to 1.3. So this is statistically significant, okay? Because 0 is not in the interval, right? Our entire interval is above 0. So, so it is statistically significant. And is it worth it? And the answer is yes, okay? It's certainly going to be worth it because our gains go from 1.2 to 1.3, which means even in the worst case, quote unquote worst case of us being down at 1.2, it's still going to be above 1.0, right? And we've got evidence that our gains are going to be above 1.0. We know they're most likely between 1.2 and 1.3. So it's going to be worth it to invest in this product. Okay? But we could also get something like this, 0.8 to 1.3, right? So 0.8, 0.8 to 1.3. You could end up getting some interval that goes from 0.8 to 1.3, all right? And so the answer, is this statistically significant? The answer is yes, it's above 0, okay? 0 is not in the interval. Anything where 0 is not in the interval, that difference is going to be statistically significant. But then the answer of, is it important or is it worth it? The answer here is maybe, maybe not, right? The true value could be above 1.0, could be as high as 1.3. But the true value could also be as low as 0.8, right? And if it's only 0.8, then it's not going to be worth it, right? It'll improve your crops. We've got evidence that it improves your crops, but is it going to be enough to kind of offset the cost of implementing everything? And the answer is, yeah, maybe not, okay? All right, so other results we can end up seeing, we could end up getting something that's not significant. Right? So you get something like going from negative 0.2 to positive 0.3, all right? So here, it's not statistically significant. 0 is in the interval. So it could be that using this particular fertilizer doesn't improve crop yields at all, right? Maybe it improves it as high as much as 0.3. Maybe it actually worsens crop yield. It actually makes it worse. You get 0.2 less. So that's possible, okay? 0 is a plausible difference value for the difference, okay? Is it going to be worth it? No, okay? Because in order for it to be worth it, it's got to be above 1.0. And even in the best case scenario, it's at best 0.3, okay? So it's not going to be above our worth it threshold. All right, and then lastly, what if the interval goes from negative 0.2? So this is possible, right? It goes from negative 0.2 all the way up to positive 1.3. All the way up to positive 1.3. Okay, so in this case, well, both 0 and 1.0 are in my interval, right? So is it statistically significant? The answer is no. 0 is in the interval, so that difference could be a 0. It could be negative. It could be positive, right? Is it worth it? Again, we don't know, right? The true value could be over 1.0. The true value could be less than 1.0. You're taking a big risk, right? If you were to try to invest in this, right? It could be, the yield could be over 1.0, but it might not be, okay? We're not sure based on this interval, right? So if your resulting confidence intervals look anything like this, whether it's statistically significant or not depends on whether 0 is in the interval or not, okay? Whether it is important or not depends on whether that particular, threshold for that determines importance, whether your interval is above that number or not, okay? All right, I hope that makes sense. All right, and so, with the second half of today's lecture, we're going to introduce hypothesis testing, okay? Hypothesis testing is kind of like well, at least for our first hypothesis test, the t-test, it's very similar to the confidence intervals that we're talking about, except we take it from a hypothesis perspective, hypothesis testing perspective, okay? So just to, again, recap the idea of statistical inference, what our class is all about, that's the process of making conclusions about the population based on a sample or samples of data, right? And so the confidence interval is a tool for statistical inference. We take a look at our sample, and in today's class, we took a look at 2 samples, and we're making a conclusion about the respective populations, population 1 and population 2, okay? Hypothesis testing is another tool for statistical inference, okay? And we can think of it as a framework that will help us make conclusions about the population. Today, we're going to introduce the t-test. It's technically the t-test for 2 independent samples, all right? And it's kind of one of our most basic hypothesis tests. And it relates directly to the confidence interval that we introduced, mu1 minus the confidence interval for mu1 minus mu2. The 2 things are mathematically equivalent, okay? But this idea of a hypothesis test, this framework for a hypothesis test, is going to be important. We are going to look at more hypothesis tests in the coming weeks. We'll look at the chi-squared test and ANOVA and the test for significant correlation and things like that. And those are all different hypothesis tests, but we approach them a little bit differently. We've got non-parametric ones, the Wilcoxon-Mann-Whitney, the sign test, things like that. Okay. But we're going to start off with the t-test, which is pretty much the same thing as mathematically is equivalent to this confidence interval for mu1 minus mu2, but we're going to be working through the hypothesis test framework. All right, and we're going to spend a lot of time talking about this hypothesis test framework and kind of the conceptual ideas that go along with it. That's going to be Wednesday's lecture. And once we establish that, then we can start looking at a whole bunch of other kinds of hypothesis tests. Okay, so the key idea and the reason why we call this hypothesis tests is that whatever research question we have, right? Like, is the medicine effective? Is there popular support for this candidate? Is whatever question it is you're trying to answer, we're going to we have to state it as a testable hypothesis. Okay, and the hypothesis that we're going to test, this is known as the null hypothesis, And what we do is we take that null hypothesis and we test it against the data we observe, right? That's the whole idea of hypothesis testing. We're going to test this premise against the data we observe, right? And in order for a hypothesis, some kind of statement or claim to be testable, it has to be a specific claim, right? It has to say, this is what the population has this exact property, okay? Otherwise, we can't test it. If If it's just going to be some vague generalizable generalization, it's going to be very difficult to test. Okay, so for example, you know, whatever you believe about, psychics and seances and stuff, if you talk to one and they just make some vague statement, right, like you will meet a mysterious person in the coming days, that's so vague that there's no way it can be tested. Right, it's just like any person you meet, like, what do you mean by mysterious and what do you mean by coming days? It's too vague to be tested, right? On the other hand, if somebody makes a prediction and says, on September 3rd, you will meet somebody wearing a yellow shirt and a gray hat, and their name will start with the letter K, that's testable, right? That's a very specific claim, and and you can say, okay, well, let's see if this actually happens or not, right? And if that does happen, you'll be like, wow, this person actually did have the power to see the future, or knew something that was going to happen, right? And so in order for a hypothesis to be testable, it has to be a specific thing. We can't just have some general thing, right? So as far as the t-test goes, which is the hypothesis test we're looking at, the null hypothesis that we are going to test is going to make this very specific claim, which is population 1 has mean mu1, and it is exactly equal to the mean of population 2, mu2. So the claim is that the two populations have the exact same mean. And because it's a specific claim, we can test this, okay? The two populations have the exact same mean, and we're going to test that. All right, and so the way the test works is we make an assertion. We say, let's assume that this claim made by the null hypothesis is true, right? Let's assume that mu1 is actually equal to mu2. Let's assume population 1 and population 2 do have the same mean. And then we say, well, if that statement is true, okay, if this hypothetical situation is true, right? We have a hypothesis that mu1 is equal to mu2, and so we imagine this hypothetical situation, and we say, if that were the case, then what would the world look like, right? What would the world look like? What would our data look like? Okay, so if population 1 and population 2 both have the same mean, when we take random samples drawn from the populations, okay, in this kind of hypothetical scenario, when you do that, your sample 1, which comes from population 1, and sample 2, which comes from population 2, those two samples should have sample means that are close to each other. If they're not exactly equal to each other, they should be at least very close to each other, right? Because the hypothesis says population 1 has mean mu1, and that's equal to population 2's mean mu2, right? These two populations have the same mean, and if I take a random sample from this population, a random sample from this population, then the sample, the mean of this sample and the mean of this sample should be pretty close to each other, okay? But then when we look at the data, right, we're going to test that hypothesis against our data. When we look at our actual data, this sample has a mean of 28.2, and this sample has a mean of 24.3, right? The two samples we've observed don't actually have the same mean, but there's a difference. There's a difference of 3.9 points, 3.9. And the question is that possible? Could this happen if the null hypothesis were true, right? If the null hypothesis were true in this hypothetical scenario, the means should be close to 0, or I mean, the difference between the means should be 0, but I'm getting a difference of 3.9, right? Is that possible? And if it's possible, what's the probability that we get this result of 3.9, right? So we say, all right, my two samples, they're subject to randomness. It was a random sample, sample 1, random sample, sample 2, right? So even if you do have two populations where the mean are the same, we can't expect the two samples to have the exact same mean. Could randomness produce this difference of 3.9? Okay. And so we want to turn this into a probability question, and that's going to be, what's the probability that just randomness alone could produce a difference of 3.9 or something more unusual if the null hypothesis were true? And that probability is known as a p-value, okay? That probability is known as a p-value. So the p-value, it has this definition, and it's the probability of observing the statistic in our data or something more unusual if we assume that the null hypothesis is true. So in the context of our problem, where sample 1 had mean 28.2 and sample 2 had mean 24.3, right? The p-value is, what's the probability of getting this difference of 3.9, okay, because that's the difference I observed in my samples, if this hypothetical situation, if the null hypothesis were true, if population 1 and population 2 have means that are equal, right? So if you have two populations with equal means, could random sampling produce one sample where the mean is 3.9 higher than the other random sample? That's kind of our question. Does that kind of make sense, this idea? And so let's say we go through the math and we say, all right, you know, we can do the math and we can say, all right, even when two populations do have the same mean, by random chance, sometimes you get different samples, or you're going to get different sample means. How often do we get a difference of 3.9? Okay, and let's say you go through those calculations and that probability turns out really small, right? It says, so one possibility is you say, well, if the two populations have an equal mean, it should be almost impossible, right? Not impossible, but it's like the probability of getting a difference of 3.9 is like 1 in 1,000, okay? It could happen by random chance, but it's really, really, really rare. It's going to happen like 1 in 1,000 times. 1 in 1,000 times, you'll get one random sample where the mean was like really high, like 28.2, and 1 in 1,000 times, you'll get another sample where the other mean is really low, like 24.3, producing this difference of 3.9. So it could happen, but it happens only in about 1 in 1,000 times. All right. So, but that's what we have in our data. We have a difference of 3.9, right? And so if the p-value ends up being small, we're going to say, well, I guess I could have been the 1 in a lucky 1,000 that got this difference of 3.9. Or perhaps the more likely explanation is that the claim made by the null hypothesis is wrong. That the reason why I'm getting this difference of 3.9 isn't that I was the lucky 1 in 1,000, but rather population 1 has a mean that's different than population 2. Okay, if population 1 has a mean that's different than population 2, that explains why I got a difference of 3.9. All right, so we're going to say, you know, if you go through the calculations, it says, you know, if the population means are equal, a difference of 3.9 is unlikely to be observed. Like maybe it happens 1 in 1,000 times. So the fact that we did observe a difference of 3.9s, which is said to be unlikely, right? It should only happen 1 in 1,000 times. We're going to say, you know what? I don't think I was that 1 in 1,000. Instead, we're going to conclude that the claim made by the null hypothesis is wrong, right? That the reason why we see a difference of 3.9 is that the means of the populations aren't equal to each other. That's a lot more easier to grasp and understand than to say, no, the two populations do have an equal mean, and it's just we got this 1 in 1,000 really lucky scenario where our difference ended up being 3.9. Okay, so we're going to just say, you know what, the two populations have different means, and so we're going to reject the claim made by the null hypothesis. We're going to conclude that the two populations have different means. Okay, does that make sense? That logic there, that our data had a big difference, and according to the calculations, you know, while not impossible, it's very unlikely to get this by just random chance. Okay, so that's one possible scenario. Okay, the other possible scenario, something happened. Okay, the other possible scenario is you do your calculations, and the probability ends up being very large. Okay, so you know, we get a difference of 3.9, right? And the results show that, you know, even if the population means are equal, okay? Because of random chance, sometimes, yeah, by random chance, you get one sample where the mean is high and the other sample where the mean is low. And, getting a difference of 3.9, yeah, it's not, the difference isn't zero, but it's also not astronomically huge. That's another possible scenario, right? We can say, the null hypothesis states that, mu1 and mu2 are equal, and we expect the difference, y bar 1 minus y bar 2, to be close to 0. What we got a difference of 3.9. That's more than 0. But when you do our calculations, it says, this kind of difference isn't that unusual, right? So that's another scenario, right? So maybe you get a p-value of like 25%. It doesn't happen all the time, but it's also not that unusual, right? It happens 1 in 4 times or something. So in that case, we're going to say, well, we don't have any reason to believe that mu1 is actually different from mu2, okay? Because if mu1 and mu2 are the same, it could still produce a difference of 3.9 just by random chance. Okay, it doesn't mean that mu1 is actually equal to mu2, right? We're not saying that. We're just saying that if mu1 and mu2 were equal, that kind of setup, that hypothetical scenario, could still produce differences of 3.9. Okay, at this point, we just don't have enough evidence to go against that claim, right? And so our conclusion here is we're not going to reject the claim made by the null hypothesis. Okay. So whether we decide to reject the null hypothesis or not is going to depend on how large our p-value is. And what we do is we compare our p-value to some chosen significance level alpha. Okay, so is our p-value considered large or small? Depends on the significance level alpha, right? If the p-value is less than alpha, then we're going to say the p-value is small. If the p-value is greater than alpha, then the p-value is considered to be large. If the p-value is considered to be small, meaning the p-value is less than alpha, what we're saying is our data is unlikely to be observed if the null hypothesis were true. And so the fact that you do observe this data, which is said to be unlikely, leads us to reject to the null hypothesis. Okay. And on the other hand, if the p-value is large, okay, meaning it's greater than alpha, then that means, even if the null hypothesis were true, our data is not considered to be unusual. And therefore, we don't have any reason to believe that the null hypothesis is wrong, and we don't reject the null hypothesis. Okay. The choice of the significance level alpha is often arbitrary. Okay. A very common choice for alpha is 5%. Okay. For better or worse, yeah, the most common choice for alpha is 5%. Probably just it probably should be something around there, but yeah, maybe not. Okay. Another common choice I would say is alpha is 1%. So people might be a little bit more conservative in terms of, or cautious in terms of whether they want to reject or not reject the null hypothesis. And so they might, be a little more cautious and use alpha only 1%. Okay. You can also have something like alpha 10%, but I would say that's fairly rare. You don't generally see alpha 10% very often. Okay. When we write our hypotheses, it's important to remember that hypotheses are always statements about the population. Okay. We never make statements or hypotheses about samples. So our hypothesis will never say something about the sample mean is this or that. It's always going to be about the population. Okay. And the null hypothesis is always the hypothesis that you are testing. And the null hypothesis will always have an equal sign, always have an equal sign. Okay. There's the hypothesis, null hypothesis is paired with what's called an alternative hypothesis. Okay. And the alternative hypothesis has to be kind of the outcome, what must be true if it turns out that the null hypothesis is wrong. Okay. So alternative hypotheses can be non-directional, which we can say that's a two-sided alternative. Okay. or they can also be directional, also known as a one-sided alternative, okay? And whether you use a directional or a non-directional one-sided or two-sided alternative hypothesis depends on the question and how the question is written. And so you kind of have to pay attention to what the question says, okay? So for example, okay, we could say the null hypothesis is that mu1 is equal to mu2, right? And this is always going to be the case for a t-test for independent samples. The null hypothesis is always going to be mu1 equal to mu2. Okay, we're going to have different t-tests where you have different hypotheses, but if you get a t-test for independent samples, this is the null hypothesis. Mu1 is equal to mu2. Okay, and that's the claim that says the two populations, population 1 and population 2, those two populations have the same mean. Okay, we could ask, do we have evidence that the populations are different? Okay, and so we could say, are they different? And in that case, you would have a non-directional alternative, meaning it would be interesting to you if mu1 was bigger than mu2. It would also be interesting to you if mu1 is smaller than mu2. So whether mu1, you just want to know if there's a difference. Is there a difference? Is mu1 bigger than mu2 or is mu1 less than mu2? Either of those things would be interesting to you, okay? But in some cases, and I'll show you an example, you're only interested in one side of the alternative, okay? And in that case, you would use a directional alternative, right? So you could have an alternative where mu1 is greater than mu2. You're only interested if population 1 has a greater mean than population 2. Or you could have mu1 less than mu2. You're only interested if population 1 has a mean that is less than the mean of population 2. Okay, so here's an example where you would have a directional alternative hypothesis, right? So let's say you're working at a pharmaceutical company, and this company says, we want to work on medication that's going to lower blood pressure. Okay, we want medication that's going to lower blood pressure, right? So population 1 could be people taking medication, and population 2 could be people taking placebo, right? And so we're interested if the product helps reduce blood pressure. So perhaps your null hypothesis will be that the drug is no different than placebo, that mu1 is equal to mu2. Okay, mu1 is equal to mu2. That's going to be your null hypothesis, that there's no difference between the drug and placebo. Okay, all right. So population 1, again, is the people taking medication. Your alternative is you want to see if this medication to reduce blood pressure is actually working. Okay, your alternative is going to be that the people using the drug have lower blood pressures than those who receive placebo, right? We want to see mu1 less than mu2, okay? Right? If it turns out that the opposite is the case, then we've got a problem. We're not interested if the medication actually increases blood pressure, right? So if that happens in the data, right? If you take your data and you end up with the mean y bar 1 being greater than y bar 2, meaning that the mean blood pressure of people using the drug is actually higher than the mean blood pressure of people using placebo, that's a problem, right? Then in that case, there's no sense in bothering to continue your analysis, right? The whole point of the study was to see if the medication helps reduce blood pressure. And when we take a look at our data, if anything, it seems like the blood pressure is increasing the medication is increasing the blood pressure, okay? There's no sense to see like, oh, maybe we need to do more statistics if this could be a result of random chance. No, there's no sense of that. We're just going to say, all right, based on the data we have, we don't have evidence supporting the idea that the drug is effective at lowering blood pressure, okay? You know, probably the pharmaceutical company would be interested to see a little bit more like why and figure that out. But as far as trying to do statistics to see, you know, could this be the result of random chance or not? You know, there's no sense in bothering that, okay? We're just going to say we have no result. The results do not support the alternative, okay? We have no evidence to support the idea that mu1 is less than mu2, okay? If anything, perhaps it supports the opposite, okay? Because y bar 1 ended up greater than y bar 2. So, you know, perhaps the opposite's the case, but you know, in this scenario, we're setting up our alternatives hypothesis because we really just want to see if the medication reduces blood pressure there. Okay. Does that kind of make sense as far as having a directional alternative? So you're going to have to read the questions, and a lot of times the questions will say, test this hypothesis against the alternative that this group is greater than the other group, or this group is less than the other group, or something like that. Okay. If the question just says, test it against, to see if there's a change, if there's a difference, those would be non-directional, right? You just, a change or difference could be something increases or decreases. Okay. And in other cases, the questions will say, we want to see if it has gotten larger or if it has gotten smaller. And in those cases, you use a directional alternative. All right, so let's revisit this problem with the the perfection game and people doing the blocks, fitting them into different shapes, and we got the young adults and we have the seniors. Okay, and here we want to perform a t-test to see if there's a difference between the mean number of blocks completed in the time span. So again, the the companies gave this dexterity test to the applicants, and we have young adults and we have the seniors. The mean completed by young adults is 28.2. The mean completed by seniors is 24.3. Standard deviation of this and this. And we're going to perform a t-test to see if there's a difference between the mean number of blocks completed in the time span. So here, we're just interested if one group is either larger or smaller than the other group. And this is not directional. We're not trying to see if one group, if the young adults can perform better than the seniors or something like that. Here, we're just looking for a difference. Okay. So first, when we establish, we got to write our hypotheses. Okay. So we're going to say mu1 represents the mean number of blocks completed by young adults. Mu2 is going to represent the mean number of blocks completed by the seniors. So our null hypothesis, again, always has an equal sign. And it's going to state that the two groups have the same population mean, that mu1 is equal to mu2. That's what our null hypothesis states. Okay. The alternative is going to be that the two groups have a different mean. Mu1 is not equal to mu2. Mu1 is not equal to mu2. That's going to be the alternative. All right. So again, we're interested if the young adults, if the seniors can complete more than the young adults. We're also interested if the seniors complete fewer than the young adults. Okay. Either of those outcomes would be interesting to us. All right. So we'll go and we'll conduct the t-test to calculate our p-value. All right. So let me go ahead and do this. All right, so we have young adults, we have seniors. Let's switch. All right, so we have N1 equal to 20, N2 equal to 15, y bar 1 equal to 28.2, y bar 2, 24.3, S1 equal to S1 equal to 4.3, S2 equal to 5.7. Okay, and then our hypotheses, null hypothesis, mu1 is equal to mu2. The alternative, mu1 not equal to mu2. Okay, so we're going to go and we'll calculate the p-value. So first, we're going to figure out our standard error. S1 squared over N1, S2 squared over N2, right? And, we've done this before, but I'll go ahead and I'll do this again for good measure. 4.3 squared over 20, 5.7 squared over 15. 1.758. Okay. And the idea here is if the null hypothesis were true, this is the distribution of the quantity y bar 1 minus y bar 2. Okay. If the null hypothesis were true, we would expect that quantity y bar 1 minus y bar 2 to be close to 0. And what we're getting is we're getting a difference of 3.9. Okay. So when we calculate y bar 1 minus y bar 2, we get 28.2 minus 24.3. We get a difference of 3.9. Okay. And so the question is how significant, how different is this? And what's the probability we get a difference of 3.9 or something more extreme? And also we want to know, well, negative 3.9 and something more extreme. What's the probability of ending up out here? Okay. And so we're going to basically get kind of like a z-score, but because it's the t distribution, we're going to call it a t, right? So how far is this from the mean in terms of standard deviations? Okay, so we're going to take that difference y bar 1 minus y bar 2. The mean is 0, so I mean I could subtract off 0, but I don't have to. And we're going to divide this by the standard error. Okay, so we're going to get 3.9 divided by 1.758. This is 3.9 divided by 1.758. This is 2.218 standard deviations away, or 2.218 standard errors from the mean. Okay. Okay. All right. So far, does that kind of make sense? So here, this is the difference we observed. We observed a difference of 3.9. If the null hypothesis were true, we would expect y bar 1 minus y bar 2 to be close to 0. We're getting a difference of 3.9. And we want to know how unusual is that, okay? So here's just kind of the calculations, right? And so what we want to know is, okay, what's the p-value? What is the area associated with 2.218? What's the area associated with 2.218? Okay, so we need to figure out the degrees of freedom. Degrees of freedom, again, we're going to approximate using n1 plus n2 minus 2. We get 33 degrees of freedom. We don't find 33 degrees of freedom directly in our table. We round down and we use 30 degrees of freedom. Same kind of idea there. Okay, and so this is what the t distribution looks like. The t distribution looks pretty much like the normal distribution. It's just a little bit, what we say, we have wider tails than the normal distribution. Okay, and here this line is drawn at positive 2.218, and again we want the area to the right of positive 2.218. I also drew a line at negative 2.218, and we want the area to the left of negative 2.218. So we want the area over here, we want the area over here. And what I'm going to do is we're going to zoom in right here because I want to kind of explain how the t-table works, because the way the t-table works is different from the way the normal table works. Okay, the normal table is quite different from the t-table. Okay, so I'm going to zoom in into this kind of corner of the t distribution, right? And if you zoom in, okay, so if I zoom in onto this row for 30 degrees of freedom, okay, I kind of cut and paste it here. So at 30 degrees of freedom, the first number is 0.854, and I have 1.310, 1.697, 1.812, 1.955, 2.042, 2.147, so on and so forth. And then kind of the corresponding, at the very top, they have what says upper tail probabilities, okay? So I just copied that top column, top heading row, upper tail probability, and the corresponding row for 30 degrees of freedom. Is this okay? All right, and so what this says, and let me zoom in here, okay? So these numbers, okay, this number here is 1.955 and the corresponding column heading is 0.03. And this number over here is 2.147, and the corresponding column heading is 0.02. Okay, so this picture says if you draw a line at 1.955 and you shade everything to the right, the amount you'll shade is 3%. Okay, if you go farther away from zero, you go farther out to 2.147, okay, 2.147, and you shade everything to the right of 2.147, the amount that you've shaded here to the right of 2.17 is going to be 2%. And if you go even farther away to 2.457, the amount that you shade to the right of 2.457 is 0.01. Okay, so the idea here is if you draw a cutoff line at any one of these values, and you say, well, how much is beyond there? If I shade beyond that line, how much am I shading? That's going to be the upper tail probability, right? So that's why as you go farther away from zero, right? So if you're at 0.854, which is pretty close to zero compared to the other numbers, you're shading in 20%. As you go farther away to 1.3, you shade only 10%. If you go farther away, 1.697, you shade only 5%. Okay, and as you go farther and farther and farther away, the amount you shade in the upper tail gets smaller and smaller and smaller. Okay. Does that kind of make sense how this table works? Right? It's saying if you draw the line here and you shade everything to the right, okay, the amount you're shading to the right gets less and less and less the farther away you get from zero. Okay, and so this is what we have. Okay, so at 2.147 we shade in 2%. At 2.457 we shade in 1%. Okay, all right, so where did we end up? Okay, so I'm going to zoom in a little bit further here. Okay, so let's look at this. We've got 2.147 is 2%, 2.457 is 1%. Okay, so if I draw a line at 2.147, I shade everything to the right, I get 2%. If I go farther away to 2.457 and I shade everything to the right, I shade in 1%. And here, our test statistic, the t-value ends up being 2.218. 2.218. Okay, and the question is what's the area to the right of 2.218? If I draw a line at 2.218 and I shade everything to the right, how much am I shading in? Okay, and so the answer is well, I can't tell. Okay, I don't know exactly what that area is, but from the picture, and just from the table, I do know that whatever number area it is, it has to be more than 1%, but it also has to be less than 2%, right? Because my number 2.218 is in between 2.147 and 2.457. So the corresponding area has to be in between 1% and 2%. Okay, does that kind of make sense? The tail area, the total, the area in the upper tail to the right of 2.218 has to be something between 1 and 2%. Okay, great. All right, and so again, this area, I don't know exactly what it is, but this area, whatever it is, has to be somewhere between 1 and 2%. So it's less than 2%, more than 1%. Okay, same thing over on this side, right? So it's symmetric. So this area also has to be between 1% and 2%. Okay, so I have this area is between 1 and 2%. This area is between 1 and 2%. So the total area, which is my p-value, if I add those two up, has to be between 2 and 4%. Okay, and basically that's going to be my p-value. My p-value, whatever it is, has to be between 2% and 4%. 2% and 4%. So I don't have the exact number, right? And so that's one thing about the t-table is you don't get exact numbers. You just say, okay, well, the actual number has to somewhere be between 2 and 4%. Okay? All right, let me go ahead and give you your last view quiz answer. Today's last view quiz answer is the letter B. B as in bear. B. B as in bear is the last view quiz answer. Okay, so our conclusion. Our p-value ends up being between 2% and 4%. So let's say our significance level alpha is 5%. Let's say we've chosen kind of 5% as our significance level. That's probably the most common choice for the significance level. And if that's the case, our p-value, even though I don't know the exact number, I know it's between 2 and 4%. So whatever it is, it has to be less than 5%, right? I don't know what it is. It's something between 2 and 4%, maybe 3, maybe 3.5%. I don't know. Okay. But we know it has to be less than 5%. Okay. And so that means our p-value is less than alpha. It's considered to be small. Okay. All right. So the question was, how did we get the p-value from t? Okay. So the t value that we got was 2.218, right? The t we got was 2.218. I go to my t table and I go to 30 degrees of freedom. 30 degrees of freedom. And we say, okay, well, 2.218 is in between these two numbers, 2.147 and 2.457, right? And I kind of drew these on this picture here. The 2.218, whatever it is in between the numbers 2.147 and 2.457, okay? And the t-table says, okay, well, you look at the column 2.147 and 2.457, and you go to the column headings. Those column headings correspond to areas of 2% and 1% in the upper tail. So this area has to be, whatever it is, has to be between 1 and 2%, okay? So how did I go from 1% and 2% to 2% to 4%? So the picture is, we have this, we're looking at the this symmetric image where this is a two-sided test. So this area is between 1 and 2%, and we're going to double it. This area on the right is between 1 and 2%. This area on the left is between 1 and 2%. So the total area has to be between 2% and 4% because I'm doubling the 1 and 2%. Yeah. Okay. So again, whatever our p-value is, it's something between 2 and 4%. We don't know exactly what it is, but we know it's got to be less than 5%. So we say our p-value is considered to be small. The null hypothesis says there's no difference between the population means. And if that were the case, if there's no difference between the average number of blocks completed by young adults and the average number of blocks completed by seniors, it would be unlikely to get a sample where the difference is 3.9, okay? It's possible. You could get a difference where you could get samples where the difference is 3.9, but that only happens between 2 and 4% of the time, okay? It's like 1 in 25. Anywhere from 1 in 50 to 1 in 25. Doesn't happen very often. It could happen, but it doesn't happen very often. Okay. So the fact that this did happen, we got a difference of 3.9. Okay. And according to our calculations, it says that shouldn't happen very often. What we conclude is that our null hypothesis is wrong. The reason why we're getting a difference of 3.9 isn't because we got this really lucky rare sample, but rather this premise that we started off with was wrong. That to say that there were no difference between young adults and seniors, we're going to come to the conclusion that that premise was wrong, and that's why I'm getting a difference of 3.9, rather than saying we're getting this difference of 3.9 by random chance. Okay, so we'd say our data provides evidence that in the population, the mean number of blocks completed by the young adults is greater than the mean number of blocks completed by seniors. Okay, so I know our alternative was non-directional, but we rejected that null hypothesis, and our data shows that the young adults did more than the seniors. Okay. Can you also conclude that the P total area is between 2 and 4%, or inclusive or exclusive? Yeah, so it would be exclusive. So we know it's for sure more than 2% and for sure less than 4%. And it's not less than or equal to 4%. It's definitely less than 4%. And it's definitely more than 2%. Okay, not inclusive. Okay, I wrote another example here, but in the interest of time, I'll let you guys figure it out, okay? I wrote through the work through the examples, and this one comes to the opposite conclusion that we should not reject the null hypothesis, but you can work through that on your own time there. Okay, we'll go ahead and end our lecture here for today. That will be it. Okay, so homework 3 has been posted. It's a little bit long. I apologize for that, but homework 3 is up, and you guys can take a look, and we'll talk more about hypothesis testing on Wednesday. So have a good night, and we will see you guys on Wednesday. And again, I'll have office hours after class. So we'll end here. All right. Thank you, everybody.